So what if I told you that the floor holding you up right now isn't actually doing it with physical force?
Yeah, it's a wild thought.
Right. Because you stand in a room, you feel this solid ground beneath you, and a physicist might just shrug and call it electromagnetic repulsion.
Which makes sense intuitively. It feels structural.
Exactly. Solid pushing against solid. I mean, we love to imagine the universe as this collection of, tiny impenetrable billiard balls just bouncing off one another.
Right, the classical mechanics view.
But today, we are going to completely dismantle that illusion. We are stripping away the billiard
We
balls.
really are.
We are jumping into this massive stack of research we've gathered for this deep dive, and it's a dense stack. I mean, we've got abstract set theory, the geometry of space-time, down to quantum chemistry and these super exotic magnetic states.
Oh yeah, lecture notes on theoretical physics, peer-reviewed journals on Jelisinski-Moria interactions.
Yeah.
It's a lot.
It is. But the mission today, the reason we are doing this deep dive, is to prove to you that the universe is actually held together by a minus sign.
Yeah, a literal mathematical -1.
Today, we are exploring the profound and totally reality-bending power of antisymmetry.
And honestly, the transition from thinking about the universe as just stuff to thinking about it as rules is, it's one of the most difficult leaps in physics.
It really hurts the brain.
It does. We are looking at a physical reality that isn't supported by tiny pillars or even fields of force, but by a really rigid geometric constraint.
Right.
If you take two identical particles and swap their positions, the mathematics of the universe literally spits out a -1.
Just a minus sign.
Exactly. And that single, seemingly abstract mathematical quirk bridges the behavior of light, the stability of the chair you are sitting on, and the future of ultra-dense quantum computing.
I want to make sure you, the listener, really grasp how wild this actually is. Because you'll see that the reason you don't fall right through the Earth and the strange twists of magnetic memory, they all boil down to the exact same mathematical loophole.
Yes.
So to really understand the physics, we have to start with the pure, naked math. We need to talk about relationships.
Right. Specifically, binary relations.
Yeah. So set the stage for us. What exactly is a binary relation in this context?
Well, in foundational mathematics, a binary relation is simply a defined rule. It associates elements of one set with elements of another, or with elements of the same set.
Okay.
You can visualize it as a collection of ordered pairs. We usually denote this by saying element A relates to element B.
So let's ground that with a real-world thing. If we take the relation is biologically related to, that would be a symmetric relation. Right?
Exactly. That's a perfect example of symmetry.
Because if I am biologically related to you, then by definition, you are biologically related to me. The arrow of the relationship goes both ways equally.
Right. Symmetric relations are highly intuitive. But then we introduce strict boundaries with asymmetric relations.
Asymmetric, not antisymmetric, yeah.
Right, asymmetric. An asymmetric relation dictates an absolute one-way flow. So if A relates to B, then B absolutely cannot relate to A.
Okay, give me an example of that.
A classic one from number theory is the relation is strictly less than.
Oh, sure.
If 3 is less than 5, 5 cannot be less than 3. It's impossible. Or in a human context, the relation is the parent of.
Right. If Jane is Jack's mother, Jack cannot be Jane's parent.
Exactly. It requires the relation to be irreflexive.
Irreflexive, meaning no element can relate to itself. You can't be your own parent.
Right. You can't be less than yourself.
That makes perfect sense. It's a strict one-way street.
Yeah.
But here is where the terminology gets incredibly specific. And I really want to emphasize this for you listening, because it is the entire crux of our deep dive today.
It's the whole ball game.
There is a massive structural difference between something being asymmetric and something being antisymmetric.
And the distinction is subtle in language, but it's totally explosive in mathematics.
Right.
An asymmetric relation is strict. But an antisymmetric relation, well, it contains this fascinating loophole regarding equality.
The loophole. Let's get into the formal rule for antisymmetry.
Okay, so the formal rule states this. If A is related to B, and simultaneously B is related to A, then the only possible conclusion is that A must be exactly equal to B.
Wait, let me try an analogy here to make sure we're really separating asymmetric from antisymmetric.
In for it.
Think of a legal contract. An asymmetric relation is like saying Party A pays rent to Party B. Party B doesn't pay rent to Party A. It's a one-way transfer.
Right, strict flow.
But an antisymmetric relation is more like saying party A owes $1,000 to party B and party B owes $1,000 to party A.
Oh, that's good.
The only way that resolves without actual money changing hands is if party A and party B are the exact same entity. The relation can only be mutual if the two things are identical.
That captures the logic perfectly. In number theory, the classic antisymmetric relation is less than or equal to.
Less than or equal to.
Yeah. 3 is less than or equal to 5, but 5 is not less than or equal to 3. That's the one-way aspect.
Right.
However, 5 is less than or equal to 5. The relation is mutual only because the numbers are identical. Another great example is divisibility among natural numbers.
Like dividing evenly.
Exactly.
Yeah.
If A divides B and B divides A, they must be the exact same number.
Okay, so we have this abstract logical rule, but how do we build something physical out of it? Because the theoretical physics notes we're looking at, they immediately take this logic and apply it to linear algebra.
Right, they jump straight into building matrices.
Yeah. So how does a matrix represent this?
Well, matrices allow us to take these abstract relations and turn them into geometric transformations. Let's look at continuous transformations. Specifically, there's something called the Lie algebra of the special orthogonal group.
The special orthogonal group. That's usually denoted as capital S, capital O, right? S-O-N.
Yes, exactly. And the special orthogonal group basically describes all the possible rotations in an n-dimensional space.
So moving things around in space.
Right. The Lie algebra associated with it, which is denoted by a lowercase son, describes the infinitesimal generators of those rotations.
The tiny step-by-step math that builds the rotation.
Exactly. And the defining characteristic of this space is that it consists entirely of antisymmetric matrices.
Okay, let's unpack that for a second. An antisymmetric matrix. The defining rule here is about the transpose of the matrix, right?
Yes, the transpose operation.
So if I have a matrix, which is just a grid of numbers, and I take its transpose, I'm essentially flipping it over its main diagonal.
You swap the rows and columns.
Right. The top right becomes the bottom left, the rows become columns. The mathematical rule for these rotation generators is that x transpose equals negative x.
Meaning, when you flip that grid of numbers over its diagonal, every single element must become its exact mathematical negative.
Okay, walk us through a visual of that.
Sure. If you have a value of, say, 5 in row 1, column 2,
Okay.
then when you look at row 2, column 1, the value there must be negative 5.
Got it.
The relations across the diagonal are perfect mirror images, but with flipped signs.
But hold on. Let's think about this. If you are flipping a square matrix over its main diagonal,
Right.
the numbers that are actually on that main diagonal, row 1, column 1, row 2, column 2, row 3, column 3, they don't move. They stay exactly where they are.
And that leads to a profound mathematical inevitability.
Right.
If an element stays in the exact same place during the flip, but the ironclad rule of the antisymmetric matrix says that every element must become its negative, you have to ask, what number is equal to its own negative?
Only 0. There is literally no other number. 5 doesn't equal negative 5. Only 0 equals negative 0.
Therefore, the diagonal entries of an antisymmetric matrix must be strictly exactly 0. There's no other possibility.
Wow.
Consequently, the trace of the matrix, which is just the sum of all the diagonal entries, is also strictly 0.
So it's 0 all the way down the middle.
Exactly. And this isn't just a quirky math puzzle. This specific antisymmetric grid, with its zeroed-out diagonal, it forms the geometric blueprint for how space-time handles continuous fields.
Which transitions us beautifully from pure math into physical reality. Because if we take this exact antisymmetric matrix structure and drop it into the four-dimensional Minkowski space-time of the universe.
Right, Einstein's playground.
Yeah, exactly. We don't just get an abstract geometry, we get light. We get the electromagnetic field tensor.
The Faraday tensor. It's often denoted as F mu nu in the literature.
F mu nu.
Yeah. If you want to write the equations of motion for electric charges in a way that respects Einstein's special relativity, meaning the equations look the same to all observers regardless of their constant velocity, you cannot treat the electric field and the magnetic field as separate entities.
They can't just be independent vectors floating around.
Right, you have to bind them together into this rank 2 tensor field.
Okay, the sources define this tensor, F mu nu, as the exterior derivative of the electromagnetic 4 potential.
Which is denoted as A.
Right, A. So for those of us who don't dream in calculus, let's ground this. What is this potential A, and what does an exterior derivative actually do to it?
Sure. The 4 potential A is a 4-dimensional vector. It combines the classical electric scalar potential, so think of voltage, with the magnetic vector potential.
Okay, voltage and magnetic potential jam together.
Exactly. Now, the exterior derivative is an operation from differential geometry.
Hmm.
It takes this potential and basically measures how it curls or varies across spacetime.
How it twists.
Right. The formula is partial mu I nu minus partial nu a mu.
Okay, let's look at that formula closely. You're taking the derivative of the nu component with respect to the mu direction and subtracting the derivative of the mu component with respect to the nu direction.
Yes.
Notice the minus sign in the middle there. If you swap mu and nu, you get the exact negative of what you started with.
The mathematical structure literally forces antisymmetry. F no nu must equal negative F no mu.
And because it is an antisymmetric matrix in 4 dimensions, 1 dimension of time and 3 dimensions of space, it is a 4x4 grid.
Right, a 4x4 matrix.
That gives us 16 slots for numbers. But as we just established with our math rules, the 4 slots on the main diagonal, the F10, F11, F22, F33, they must be strictly 0.
That leaves 12 slots.
But wait, if the matrix is antisymmetric, the 6 slots below the diagonal are just the negative mirror images of the 6 slots above the diagonal.
Exactly. They aren't independent pieces of information. If you know the top, you know the bottom.
That deduction is crucial. Because of the antisymmetry, the entire electromagnetic field across all of spacetime is completely described by exactly 6 independent non-zero components.
And those 6 components map perfectly onto the 3D reality you experience every day.
Which is so cool. 3 of them are the spatial components of the electric field, X, AI, and S.
Right.
And the other 3 are the spatial components of the magnetic field, BX, B, and B's.
When we write out the contravariant matrix representation, the top row and the first column are occupied by the electric field components. Usually they're divided by the speed of light, c, just to keep the units consistent across space and time.
Right, because time is sort of that 0th dimension.
Exactly. And the remaining 3x3 block in the lower right of the matrix, that is entirely populated by the magnetic field components.
So the lecture notes point out a really subtle but vital distinction here about those vectors. They say the electric field components form a polar vector, while the magnetic field components form an axial vector or pseudovector.
Yes, pseudovectors.
What is the physical difference there? Why is magnetism a pseudovector?
So a polar vector, like the electric field or velocity, represents a true direction in space.
Like an arrow pointing from A to B.
Right. If you mirror the universe, meaning if you invert all spatial coordinates through a center point, a polar vector flips its direction.
Okay, up becomes down.
Exactly. But an axial vector, like the magnetic field or angular momentum, is actually describing a rotation or a circulation.
A spin.
Right. If you mirror a spinning object, it still appears to spin in a way that its axis doesn't flip its sign under full inversion in the same way a straight arrow would.
Oh, I see.
The magnetic field is essentially the mathematical cross product of spatial dimensions, which is why it lives strictly in the 3x3 rotational block of our antisymmetric matrix.
And because these electric and magnetic fields are locked together inside this single antisymmetric matrix, we can use it to find absolute truths about the universe.
Oh, yes. Lorentz invariants.
Right. The sources talk about these Lorentz invariants. These are values that no matter how fast you are flying in a spaceship or what direction you are moving, they remain absolutely constant for everyone.
See, observers moving at different speeds will disagree on time. They will disagree on length. And they will definitely disagree on the individual strength of the electric and magnetic fields.
Right, relativity 101.
But if you take the inner product of the field strength tensor with itself,
Which means?
multiplying the matrix by itself in a specific relativistic way, so F mu nu times F contravariant mu nu, the mass simplifies down to this beautiful singular expression.
And that expression is 2 times b squared minus e squared over c squared.
Exactly.
So the square of the magnetic field minus the square of the electric field is a constant for everyone in the universe.
It is absolute reality. And another deeply profound invariant is the pseudoscalar invariant. This is formed by taking the tensor and multiplying it by its Hodge dual.
Okay, let's not lose the listener here. What exactly is a Hodge dual in this context? Are we just multiplying the matrix by a mirrored version of itself, or what?
Well, the Hodge star operator is a concept from differential geometry. It basically maps geometric forms into their complements.
Their complements.
Right. In our four-dimensional spacetime, it maps a 2 form, which our Faraday tensor is, to another 2 form.
Okay.
Physically, applying the Hodge dual to the electromagnetic tensor essentially swaps the roles of the electric and magnetic fields.
Yeah.
but also adds a sign change to maintain the geometric orientation.
So it turns E into B and B into negative E.
Exactly.
Wow. So when you multiply the original tensor by its Hodge dual, you are multiplying the fields by their swapped counterparts.
And the result of that multiplication is -4 over C times the dot product of the B and E vectors.
The dot product of the electric and magnetic fields. So if the fields are perpendicular to each other, like they are in a laser beam or any ray of light, the dot product is 0.
Right.
And it's 0 for every observer, everywhere, forever.
That is the power of the tensor. But we also have to look at what happens when you actively change your frame of reference.
Yeah, the lecture notes dive into Lorentz transformations here, specifically the boost relations.
Right. What happens to the components of this matrix when you hit the gas pedal?
And this is where my mind completely melted reading the sources. The math literally shows that the electric and magnetic fields bleed into one another.
The mixing is incredibly elegant. If you apply a Lorentz boost, meaning you accelerate to a velocity v in a specific direction, the components of the fields that are parallel to your motion, they don't change at all.
Okay, so the new E parallel is just the old E parallel.
Exactly. But the perpendicular components mix.
How did they mix?
The new perpendicular electric field is derived from the old perpendicular electric field multiplied by the relativistic gamma factor, plus the cross product of your velocity and the magnetic field.
Wait, I need to push back on this because the implications are huge.
Mhm.
Are you telling me that magnetism isn't its own fundamental standalone force of nature? Is it really just what an electric field looks like when you run past it?
Well, I wouldn't frame it as an illusion, but rather an emergent relativistic property of the electric field.
That is crazy.
As the lecture notes explicitly observe, E and B play a completely symmetric, intertwined role dictated by the antisymmetry of the matrix. There is no such thing as a pure electric field or a pure magnetic field in an absolute sense.
Because it depends on who's looking at it.
Exactly. If you hold a stationary electron, you measure a pure electric field. But to an observer driving past you in a car, that exact same electron is moving relative to them.
And a moving charge is a current.
Right. And a current generates a magnetic field. So to the moving observer, the field is a mixture of electric and magnetic.
It's like looking at a 3D shadow of a 4D object. If you rotate your perspective, which in Minkowski spacetime just means changing your velocity, you change the shape of the shadow. You trade some of the electric field for the magnetic field.
That's a great way to visualize it.
The underlying reality is just this one continuous antisymmetric tensor.
The matrix forces the fields to trade places. But that profound connection between antisymmetry and physical reality, it doesn't stop at the continuous, smooth fields of spacetime.
Oh no, we are going deeper.
We are plunging straight down into the discrete, jarring quantum building blocks of solid matter.
Right, because if this matrix math perfectly describes light and fields in a continuous vacuum, what happens when we crash into solid, discrete matter? I mean, do atoms actually care about antisymmetric matrices?
They do more than care.
The answer is literally the reason we exist. We have to look at the quantum rule book, specifically the Pauli exclusion principle.
To understand how antisymmetry builds matter, we have to travel back to 1924.
Okay, quantum history time.
Wolfgang Pauli was analyzing something called the anomalous Zeeman effect.
The Zeeman effect. That's what happens when you put an atom in a magnetic field and its spectral lines, the specific colors of light it emits, they split into multiple lines, right?
Correct. A magnetic field interacts with the orbital angular momentum of the electrons, splitting their energy levels.
Okay.
But the anomalous part was that certain atoms, like the alkali metals, showed a doublet structure.
Meaning a splitting into two lines.
Exactly. And they did this even when there was no external magnetic field applied, or in ways that the classical theory simply couldn't account for. Niels Bohr, who was the titan of quantum physics at the time,
Right, the Bohr model.
he believed that this doublet structure was caused by the angular momentum of closed inner electron shells, like the K shell.
So Bohr thought the inner core of the atom was basically spinning and causing the split.
Yeah, but Pauli proved him wrong.
How so?
Pauli demonstrated mathematically that closed electron shells have absolutely zero angular and magnetic moments. They're spherically symmetric, totally inert.
So they couldn't be causing the split.
Right. Instead, Pauli proposed a radical idea. The valence electron itself possessed a non-classical two-valuedness.
A property of the particle itself that can only have two possible states, which today we just call spin, pointing either up or down.
The introduction of spin was monumental. It led Pauli to formulate his famous exclusion principle.
Which says what?
that no two equivalent electrons in an atom can have the exact same set of 4 quantum numbers.
Okay, so if an electron occupies a definite state defined by its energy level, its orbital shape, its magnetic orientation, and its spin, that state is considered entirely full.
Yes, no other electron may enter.
But I want to explore why this actually happens, because in classical mechanics, identity is easy. If I have 2 billiard balls, one red and one blue, I can track them.
Sure.
Even if I paint them both white, I can keep my eye on ball A and ball B as they bounce around. They have continuous trajectories. I always know which is which.
But that intuition completely shatters in quantum mechanics.
Why?
Particles of the same kind, say 2 electrons, are fundamentally intrinsically indistinguishable. They do not have continuous trajectories. They're described by probability clouds, by wave functions.
You literally can't track them.
You can't. When Heisenberg and Dirac were formulating the quantum mechanics of many particle systems in 1926, they realized this indistinguishability forced the state spaces of these particles to obey strict mathematical symmetry rules.
And this is the spin statistics connection. The sources highlight this heavily. It's the grand dividing line of the entire quantum universe.
It really is. It divides all particles into 2 camps. Particles with integer spin-like photons, the carriers of light, which have a spin of 1, they're called bosons.
Okay, bosons.
Bosons must have symmetric wave functions. They love to clump together. It's how lasers work. You can pack infinite photons into the same exact state.
But the particles that make up solid matter, so electrons, protons, neutrons, they have half-integer spin, like 1/2.
Right. They are fermions.
And fermions are ruled by our favorite mathematical concept. They must have antisymmetric wave functions.
Let's translate that into the math of the wave function. Suppose you have a wave function describing a system of 2 identical fermions.
2 electrons, say.
We'll write it as psi of 1, 2, where 1 represents the coordinates of the first fermion and 2 represents the second.
Okay, psi of 1, 2.
Because they're indistinguishable fermions, if you mathematically swap their coordinates to evaluate the state psi of 2, 1, the universe demands that the probability amplitude must be multiplied by -1.
So the equation is strictly psi of 1, 2 equals negative psi of 2, 1. Swapping the particles yields the exact negative of the original state.
Yes.
But let me stop you, because there's a paradox here that trips a lot of people up. If these electrons are 100% indistinguishable, if there is literally no physical difference between them, how can the math even label them electron 1 and electron 2 in order to swap them in the first place? Isn't that breaking the rule?
It's a profound philosophical and mathematical tension. We assign the labels 1 and 2 in the mathematical formalism to construct the state space simply because our mathematical tools require syntax.
We need a way to write down the coordinates on paper.
Right. But the genius of the antisymmetric wave function is that it ensures those labels have no physical, measurable reality.
How does it hide the labels, though?
Remember that in quantum mechanics, the physically measurable thing is not the wave function itself, but the probability distribution.
Which is the absolute square of the wave function.
Exactly. If you square psi of 1, 2, you get some probability distribution. If you swap the particles and get negative psi of 2, 1, and you square that, the negative sign vanishes.
Because -1 times -1 is +1.
Right. The measurable physical reality remains completely unaltered by the swap. The labels vanish in the squaring.
So the negative sign doesn't affect the probability if the electrons are in different places. But what if we try to force them into the exact same place?
Well, then things get interesting.
Right. This is where the math becomes a physical force. How do physicists actually calculate a state for an entire atom full of electrons without accidentally violating this rule?
They use a brilliant mathematical tool called the Slater determinant.
The Slater determinant.
This is where the pure matrix math we discussed earlier crashes headfirst into quantum mechanics to literally prevent you from falling through the floor.
Okay, set up the matrix for us. How does a Slater determinant actually work?
Imagine a grid. The rows of the matrix represent the physical coordinates of the electrons, electron 1, electron 2, all the way down to electron n.
Rows are electrons. Got it.
The columns represent the available quantum states, the spin orbitals.
What's a spin orbital?
It's a combination of a spatial wave function and a spin direction. So the entry in row 1, column 1, is the mathematical function of electron 1 occupying state A. Row 2, column 1, is electron 2 occupying state A.
And the whole matrix is multiplied by a normalization constant, 1 over the square root of n factorial, just to keep the total probability at 100%.
Yes, and to find the total wave function of the atom, you calculate the determinant of this massive matrix.
And because it is a determinant, it obeys the strict, rigid laws of linear algebra. The mathematician Leibniz proved centuries ago that if you swap any two rows of a matrix determinant, the final value of the determinant changes its sign.
Think about what that physically means. Swapping two rows means you are taking the coordinates of electron 1 and swapping them with electron 2.
And the math naturally spits out a minus sign.
It perfectly enforces the fermion rule. Psi of 1, 2 equals negative psi of 2, 1. It's built into the geometry of the matrix.
But here is the catastrophic consequence of that matrix geometry. What happens if two rows are exactly the same? What if electron 1 and electron 2 are trying to occupy the exact same spin orbital state?
If two rows of a matrix are identical, the determinant of that matrix isn't just negative or positive. The determinant mathematically collapses. It is exactly 0.
Zero. The wave function vanishes identically.
A probability amplitude of 0 means the state has a 0% chance of existing. The math literally deletes the possibility of the universe allowing two fermions to occupy the exact same quantum state.
It's like the ultimate cosmic Sudoku puzzle. The rules of Sudoku say you can't put two fives in the same row. If you try to force a second 5 into that row, it's not just a bad move. The entire puzzle mathematically ceases to resolve. The state space just doesn't exist.
That's exactly it. And this mathematical 0, this structural void, is the origin of the stability of matter. It creates what physicists call degeneracy pressure.
Let's talk about that pressure. Imagine the electrostatic force. The positively charged nucleus is pulling the negatively charged electron inward. As the distance gets closer to 0, classical physics says that attractive force should approach infinity.
Right, all the electrons should just crash into the nucleus.
But they don't, because as the electrons are pulled closer, they start running out of available lower energy quantum states.
The Slater determinant forbids them from sharing states.
Right.
Therefore, the electrons are forced to occupy higher and higher energy levels, spreading outward spatially. This geometric rule acts as an outward pressure, resisting the infinite inward pull of the electrostatic force.
Which is mind-blowing.
It is. This is what stops a dead star from collapsing until gravity overwhelms it to form a neutron star. And even then, neutron degeneracy pressure takes over.
So when I knock on a wooden desk, the solid sound, the resistance I feel, I'm not feeling billiard balls hitting each other. I am feeling my hand's electrons refusing to share a Slater determinant row with the desk's electrons.
Precisely. You are feeling math. To understand how this works spatially, the quantum chemistry notes break down a simple two-electron system into its singlet and triplet states. This perfectly illustrates how the antisymmetry constraint forces particles apart.
Okay, so if we have two electrons and we assume the forces on them don't depend on their spin, a spin-independent Hamiltonian, we can factor the total wave function into two separate parts.
A spatial component, which describes where they are, and a spin component, which describes which way they are pointing.
Okay.
There are 4 possible combinations of spin for 2 electrons. One of these combinations is called the singlet state. In the singlet state, the total spin S is 0.
And the mathematical form of the singlet spin state is 1 over the square root of 2 times the state up-down minus the state down-up.
Notice the minus sign there. Because of that minus sign, if you swap the spins, the state becomes negative.
So the singlet spin state is antisymmetric.
Yes. But remember the overarching law of the universe. The total wave function for fermions, so space, multiplied by spin, must be antisymmetric overall.
Right.
Therefore, if the spin component is already antisymmetric, the spatial component must be symmetric. A symmetric space times an antisymmetric spin yields an antisymmetric total.
Okay, now let's look at the other combinations, the triplet states. In these states, the total spin S is 1.
Right.
One of the triplet states looks like 1 over the square root of 2 times up-down plus down-up. There is a plus sign. If you swap them, it stays exactly the same. The spin component is symmetric,
Which forces the inverse spatial requirement. To keep the total wave function antisymmetric, the spatial component of the triplet state must be antisymmetric. If you swap the spatial coordinates, you get a minus sign.
Okay, this is a lot of quantum accounting. Why does it matter if the spatial part is symmetric or antisymmetric? What does that actually do to the physical atom?
It drastically alters the energy of the system through the mechanism of electron repulsion.
Okay, how?
To find the total energy of these states, we integrate over their probability distributions. The energy calculation gives us 2 main types of integrals regarding repulsion. The Coulomb integral, denoted as J, and the exchange integral, denoted as K.
Let me stop you there. The Coulomb integral J, I understand. That's just classical electrostatic repulsion. 2 negative charges push each other away based on how close their probability clouds are.
Exactly.
But what on earth is the exchange integral K?
The exchange integral has absolutely no classical equivalent. When
Right.
you take the Slater determinant wave function, which is a sum of terms, and you square it to find the probability, you get cross terms.
Cross terms.
Yes, these cross terms represent the quantum interference of the indistinguishable particles. K is the energy associated with that interference.
And how do J and K affect our singlet and triplet states?
When you run the integrals, the energy of the symmetric spatial state, the singlet turns out to be the base energy plus the Coulomb repulsion J plus the exchange energy K.
Plus K.
But the energy of the antisymmetric spatial state, the triplet, is the base energy plus J minus the exchange energy K.
The triplet state subtracts K, so it has a significantly lower total energy. But why? What is physically happening in the antisymmetric spatial state that lowers the energy?
Think about the geometry of an antisymmetric spatial function. The function requires that f of x, y equals negative f of y, x.
Okay.
If both electrons try to occupy the exact same physical space, meaning x equals y, the function becomes f of x, x equals negative f of x.
Exactly. So the probability of finding the two electrons in the exact same location is identically 0. The math literally carves out a physical void between them.
We call this void the exchange hole, right?
Yeah.
The exchange hole, yes. Because the electrons in the triplet state, which have parallel spins, are forced by the antisymmetry rule to never occupy the same space. Their average physical distance from one another is larger.
And because they are further apart.
Their classical Coulomb electrostatic repulsion is drastically reduced. The system achieves a lower, more stable energy state simply because the geometry forces the electrons to avoid each other.
That is mind-blowing. The electrons aren't actively pushing each other away harder. They are just obeying a spatial traffic law that prevents them from colliding, which happens to lower their electrostatic tension.
It's purely geometric.
And this microscopic traffic law scales up. It doesn't just stabilize a single atom.
Yeah.
When we take this exchange integral K and scale it up across billions of atoms in a crystal lattice, we suddenly get macroscopic observable phenomena.
This brings us to solid-state physics and the exchange interaction, denoted as Jx. The exchange interaction is the primary physical mechanism responsible for ferromagnetism.
The magnetism you interact with daily.
Exactly. Paul Dirac, one of the founders of quantum mechanics, analyzed this. He realized that this purely spatial geometric constraint acted as if the spins of the electrons were directly coupled by a potential force.
Okay, Dirac formulated a spin-coupling Hamiltonian to model this behavior, right?
He did. The energy of this interaction is proportional to -2 JAB times the dot product of the spin vectors, SA dot SB.
The dot product. A dot product takes two vectors and returns a single number based on how parallel they are. And because A dot B is the exact same as B dot A, this is a symmetric interaction.
Yes, it's isotropic. It doesn't care which direction the spins point, only how they relate to each other.
The critical factor is the sign of the exchange constant, JAB. The sign dictates the macroscopic fate of the material.
Right. If JAB is positive, the overall energy of the crystal is lowered when the dot product is maximized. Dot product is maximized when the vectors are perfectly parallel.
So a positive JAB forces all the microscopic compass needles in the iron to line up in the exact same direction. The material becomes a ferromagnet.
Conversely, if JAB is negative, the system minimizes its energy when the dot product is minimized, meaning the spins point in exactly opposite directions.
Up, down, up, down.
Exactly. This results in antiferromagnetism. The spins form a rigid, alternating grid. To the naked eye, an antiferromagnet has no net magnetic field because the opposing spins perfectly cancel each other out.
Wait, I have to pause and challenge you here because this goes against everything we're taught in grade school. Are you telling me that the magnet currently holding a grocery list to my refrigerator isn't working because of magnetic forces?
It is a shocking realization, but the direct magnetic dipole interaction, the actual magnetic force between two neighboring electrons, is incredibly weak.
How weak?
It is about 1,000 times too weak to overcome the random thermal vibrations at room temperature. If ferromagnetism relied solely on magnetic forces, your fridge magnet would instantly demagnetize from the ambient heat of your kitchen.
So what is holding the grocery list up?
Electrostatic repulsion under a geometric constraint.
That is wild.
The fridge magnet is overwhelmingly driven by the electric Coulomb force, but structured by the Pauli exclusion principle. The atoms line up their spins because parallel spins force the spatial wave function to be antisymmetric.
And that antisymmetry creates the exchange hole.
Right. It separates the electrons, which drastically lowers their massive electrostatic repulsion. The macroscopic magnetic field of the fridge magnet is just a side effect, a massive shadow cast by the quantum alignment of electrostatic forces.
Magnetism is an emergent illusion of electric repulsion dodging a math rule. That is spectacular. And the sources quantify how strong this illusion is. They define the exchange stiffness constant, ASC.
The exchange stiffness constant measures the energy penalty for twisting the spins away from perfect alignment. It is defined as the exchange integral Jx multiplied by the expectation value of the spin squared, divided by the lattice parameter A.
Which is the distance between the atoms.
Right. It tells you exactly how rigid the magnetic order is.
But notice that the Heisenberg exchange, this dot product, only wants two things. It wants the spins perfectly parallel or perfectly anti-parallel, 0 degrees or 180 degrees. It is a symmetric relationship. But what if we inject antisymmetry back into the interactions between spins?
What if we introduce a twist?
Yeah, exactly. What happens then?
Well, this is where the physics gets intensely complicated and incredibly beautiful. We have to introduce a new term to the Hamiltonian, the Jelshinsky-Moriya interaction, or DMI.
Okay, let's break down the DMI. The Hamiltonian for DMI is written as the sum of a vector Dij dotted with the cross product of the two spins.
SI cross SJ.
Exactly. Focus on that cross product. We started this entire deep dive talking about antisymmetric matrices and relations. The vector cross product is the most famous quintessential antisymmetric operation in all of physics and 3D geometry.
If you take the cross product of vector A and vector B, the result is a new vector pointing perpendicular to both. But if you reverse the order, the cross product of B and A, the result points in the exact opposite direction.
Across B equals negative B cross A.
The cross product spits out the minus sign.
And because of that antisymmetry, the cross product is maximized not when vectors are parallel, but when they are exactly orthogonal perpendicular to each other at 90 degrees.
Therefore, the Jelshinsky-Moriya interaction does not want the spins to line up. It heavily favors a perpendicular twist.
So inside a crystal lattice, you have a massive fundamental tension. This strong Heisenberg exchange is screaming, line up parallel, and the DMI is whispering, no, twist sideways.
Historically, this interaction was introduced purely phenomenologically in 1957 by the physicist Igor Jelshinsky.
Why did he introduce it?
He was trying to solve a mystery regarding crystals like hematite, which is alpha Fe2O3, and manganese carbonate. These materials were known to be purely antiferromagnetic. The strong Heisenberg exchange forced the spins to perfectly alternate, up, down, up, down. So they shouldn't have any net magnetic field at all. Exactly. Yet experimentalists repeatedly measured a very faint, spontaneous magnetic moment in these crystals. It was dubbed weak ferromagnetism.
And Jelshinsky realized that a theoretical antisymmetric interaction could explain this. The DMI forces a slight canting, a tiny fraction of a degree tilt in the antiferromagnetic lattice.
Because the opposing spins are tilted slightly toward each other, they no longer perfectly cancel out. A tiny net magnetic moment escapes.
So Jelshinsky guessed the math, but he didn't know the physical mechanism, right?
Right. 3 years later, in 1960, Tor Moriya provided the microscopic theory. He explained why the atoms were twisting.
Okay, what was Moriya's theory?
Moriya proved that DI emerges from the combination of two complex phenomena, superexchange and spin-orbit coupling.
Superexchange is an indirect interaction where two magnetic atoms communicate their spin states through an intermediate non-magnetic atom, like an oxygen ion between two iron ions.
Exactly. And then there's spin-orbit coupling.
We need to unpack that. How does relativity twist a magnetic spin?
As an electron orbits a heavy nucleus, it is moving incredibly fast, a significant fraction of the speed of light. Because of the Lorentz transformations we discussed earlier, from the perspective of the moving electron, the stationary electric field of the nucleus transforms into a magnetic field.
Okay, I'm tracking.
This induced relativistic magnetic field interacts with the electron's own inherent spin, that is, spin-orbit coupling. It tightly links the spatial movement of the electron, its orbit, with its internal quantum state, its spin.
So when the electron communicates its spin to a neighboring atom via superexchange, the spin-orbit coupling acts like a funhouse mirror. It twists the signal. The neighboring atom receives a spin vector that has been rotated.
Precisely. Moriya's microscopic theory was a triumph because it allowed physicists to analyze how the direction of the twist, its chirality, whether it rotates left or right, depends entirely on the quantum occupation of the heavy transition metal's third electron shell.
The sources mention that calculating this DMI vector, Dij, is an absolute computational nightmare. You can't just write out a simple equation. You have to use first principles density functional theory, or DFT.
DFT is a method that determines the properties of a many-electron system, not by calculating the impossibly complex multidimensional wave function, but by analyzing the spatially dependent electron density.
Which is easier to calculate.
Exactly. To calculate DMI, physicists have to use DFT combined with correlated band theory and Green's functions.
Green's functions basically measure the impulse response of the quantum system, right? How a disturbance in one part of the electron cloud propagates to another.
Yes. They use the magnetic force theorem to evaluate the anticommutator of the total moment operator with the hopping integrals of the electrons. It requires supercomputers evaluating immense, dense matrices just to figure out which way a microscopic spin decides to tilt.
But that dense math is vital. Because what happens when DMI gets strong? What happens when the antisymmetric twist seriously competes with the symmetric Heisenberg alignment? You don't just get a tiny fraction of a degree tilt.
Oh no, you get entirely new, complex topological states of matter.
Which leads us to the final frontier in our sources. Skyrmions and hidden DMI.
When the DMI is strong enough, it twists the spins into stable, microscopic tornadoes called magnetic skyrmions. Imagine a two-dimensional grid of spins. At the outer edges of the vortex, all the spins point straight up. As you move toward the center, the spins gradually tilt inward, rotating smoothly until you reach the exact center core where the spin points perfectly straight down.
It's a topological knot. The spins are locked into this continuous whirl, and because you can't smoothly deform that knot back into a perfectly parallel state without breaking the spins, without expending a massive amount of energy, the skyrmions is topologically protected. It's incredibly stable.
For decades, physicists believed skyrmions could only exist in a very specific, narrow class of materials, crystals that lacked an inversion center.
Let's define an inversion center. Imagine the center of the crystal lattice. If you can draw a line from any atom through that center point and find the exact same type of atom at the same distance on the other side, the crystal has global inversion symmetry. It is centrosymmetric.
The rigid rule in solid-state physics was that DMI is strictly forbidden in centrosymmetric crystals. If the crystal is perfectly symmetric globally, the antisymmetric twists of the DMI vectors must perfectly cancel each other out, leaving a net DMI of 0. No DMI, no skyrmions.
But the nanoletters paper in our stack drops a massive, field-altering plot twist. It details the discovery of hidden DMI.
Recent high-level studies have shown that global symmetry is an illusion that hides local chaos. Even if the crystal lattice as a whole is perfectly centrosymmetric, specific spin sublattices within it, local neighborhoods of atoms, might break inversion symmetry locally. This phenomenon is called local inversion symmetry breaking, or LISB.
Think of a grand ballroom dance viewed from a high balcony. The room is a perfect circle, and there are hundreds of couples dancing. From above, the entire floor looks perfectly balanced, perfectly symmetrical. For every couple on the left, there is a couple on the right doing a mirrored step. The global structure is symmetric,
Right.
but if you jump down to the floor and zoom in on just one specific pair of dancers, they are actually doing a fiercely asymmetrical, twisted tango. They are breaking the symmetry locally. The local twists cancel out globally, so the room looks calm, but locally, those twists create powerful, swirling forces.
That localized twisted tango creates hidden DMI. Because the local symmetry is broken, the antisymmetric spin-orbit coupling generates massive DMI vectors that govern those specific atoms. And this hidden DMI favors separated skin spirals with opposite chiralities, some twisting left, some twisting right.
And this hidden twisting leads to completely novel topological structures. The sources discuss observing anti-chirality-locked merons.
A meron can be thought of as a half skyrmion. Instead of the spins pointing up on the edges and down in the center, a meron's core points down, but its outer edges point radially outward in the geometric plane. The papers observed chains of these merons, forming ferromagnetic meron chains in materials like barium cobalt sulfide, driven by the Rashba effect. The Rashba effect being a momentum-dependent splitting of spin bands in two-dimensional systems where the structural symmetry is broken. But let's bring this back to the listener. You might be wondering, why do we care about a microscopic half-tornado of magnetism in a speck of barium cobalt sulfide? Why spend supercomputer hours calculating Green's functions for a twist?
We care because of the future of human technology. Skyrmions and merons are incredibly small, topologically stable, and most importantly, they can be pushed around the crystal lattice using microscopic electrical currents. They are currently the prime candidates for racetrack memory in quantum and spintronic computers. Traditional hard drives spin magnetic platters and read the domains. It's bulky and takes a lot of power. Racetrack memory would use a solid, unmoving wire. The data is encoded as skirmions. A skirmion is a 1, no skirmion is a 0. You apply a tiny current, and the tornadoes march down the wire in a neat little line past a read-write head.
You could pack data orders of magnitude more densely and move it with a fraction of the power, generating almost no heat. But we were limited by the belief that we could only build them out of asymmetric crystals. Unlocking hidden DMI and globally symmetric crystals blows the doors off the materials science lab. It vastly expands the catalog of metals, insulators, and 2D materials we can engineer to build the ultra-efficient computers of tomorrow.
And all of it, every single bit of it, traces back to the exact same mathematical loophole. Let's summarize the journey we just took. We started with the pure, naked logic of an antisymmetric binary relation. The rule that A relates to B, B relates to A, only if A equals B.
We encoded that rule into a matrix. The transpose must equal the negative, which forces the diagonal to be exactly 0.
We dropped that matrix into the geometry of space-time, and it bound the electric and magnetic fields together into the Faraday tensor, proving that magnetism is just the relativistic shadow of a moving electric field.
We brought that antisymmetry down into the quantum realm, where the fundamental indistinguishability of fermions demands an antisymmetric wave function.
We calculated that wave function using the Slater determinant. Because the diagonal is 0, identical states vanish. Two electrons cannot share the same reality. The Pauli exclusion principle forces the electrons apart.
That forced spatial separation creates the exchange hole, lowering the electrostatic Coulomb repulsion, which manifests macroscopically as this symmetric Heisenberg exchange interaction, the very ferromagnetism holding your grocery list to the fridge.
But when you add the relativistic twist of spin-orbit coupling, you get the antisymmetric cross-product back, the Dzieloshensky-Maria interaction.
Which twists those spins into topologically protected tornadoes, hiding inside globally symmetric crystals, ready to power the next revolution in data storage.
It is breathtaking. Your solid, stable existence, the light hitting your eyes, the chair supporting your weight. It all depends on indistinguishable electrons obeying an abstract geometric math rule that absolutely refuses to let them share the exact same quantum state. The universe is literally held up by a minus sign.
It is the ultimate triumph of mathematical geometry over physical intuition. We are creatures living in a reality built by constraints, not by building blocks.
It really changes how you look at everything. But I want to leave you, the listener, with a final, highly provocative thought. We've spent this entire hour talking about the strict, ironclad division of the three-dimensional universe. You are either a symmetric boson that loves to clump or an antisymmetric fermion that refuses to share space. There is no middle ground in 3D, but the deeper mathematical sources hint at a loophole in the topology of the universe.
The rules change fundamentally when you restrict particles to moving in strictly two spatial dimensions.
In a 2D plane, the topology doesn't require a strict sign flip of +1 or -1 when particle swap. The math allows for a continuous phase shift. It allows for a spectrum between fermions and bosons, a concept known as fractional statistics. The particles that obey these fractional rules are called anyons.
Anyons can remember how they have been braided around each other. Their quantum state depends on their topological history.
If the rigid black and white rule of antisymmetry builds our entire stable 3D world, the very floor under your feet, what completely alien mind-bending physics and structures are hiding in microscopic 2D materials where that rule is finally allowed to bend? What does a universe built on fractional statistics feel like? It is something to ponder the next time you trust the floor to hold you up.